We've got some fresh images of 3I Atlas, a third ever interstellar object.
3I Atlas was discovered on July 1st.
The discovery surrounding 3I Atlas has drawn extraordinary attention in the scientific community, and the James Webb Space Telescope has just provided a revelation that has deepened both the mystery and the wonder surrounding this interstellar visitor. Initial observations had already suggested that this object, the third confirmed interstellar traveler to pass through our solar system, was unusual. Yet now, with the unmatched sensitivity of the James Webb, astronomers have realized that 3I Atlas is much larger than anyone anticipated. This confirmation has forced scientists to rethink earlier models of its structure, its trajectory, and even its potential place of origin in the broader galaxy. What seemed like another brief encounter with a foreign object drifting through the Sun's neighborhood has transformed into an event of immense importance for understanding the formation of planetary systems across the stars. Before we start, smash the like and subscribe buttons for more updates. The context of this discovery rests on the history of interstellar objects detected so far. The first was 1E Oumuamua, a long, elongated, and enigmatic body that sparked debates about its composition, and whether it was comet-like, asteroid-like, or something else entirely. The second was 2I/Borisov, which displayed the more familiar characteristics of a comet, with a visible tail and outgassing patterns that aligned with expectations. 3. I. Atlas was thus anticipated with great curiosity, as each new interstellar object offers a rare opportunity to examine matter born beyond the solar system. Unlike planets or comets that formed alongside Earth and its siblings, these interstellar objects are fossils from alien environments, potentially billions of years old. The Webb's revelation that 3I Atlas is significantly larger than expected adds a new dimension to this unfolding story, one that could reshape how we view the processes that eject these bodies from their home systems. When 3I Atlas was first tracked, astronomers estimated its size based on the brightness and behavior of the object as it reflected sunlight. Those estimates suggested something within the typical range of smaller comets, perhaps tens to a few hundred meters in scale. However, the James Webb Telescope, with its infrared capabilities and ability to cut through the distortions of distance and faint light, has revealed that 3I Atlas is several times larger than early predictions. The implications of this are profound. A larger size means more mass, which means the gravitational and dynamical story of its ejection and journey across interstellar space becomes more complex. It also suggests that interstellar objects might not be limited to tiny fragments or faintly glowing debris, but could include robust and massive chunks of planetary material. This increase in size challenges some earlier theories about how such objects escape from their parent systems. Smaller bodies can be expelled more easily by gravitational interactions with giant planets or the movement of stars in densely packed regions. Larger objects, by contrast, require more energetic scenarios. One possibility is that 3I Atlas may have originated in a system with massive gas giants that acted as slingshots, hurling enormous comets or asteroids into interstellar space. Another is that it may have been part of a catastrophic planetary collision in some distant system, shattered into fragments and flung outwards, with 3I Atlas surviving as one of the larger remnants. Each scenario opens up fascinating avenues of speculation about the diversity and violence of planetary formation in the galaxy. The Webb's data also provide a better understanding of the surface composition of 3I Atlas. Its infrared spectrum suggests the presence of volatile ices mixed with darker, carbon-rich materials. These findings indicate that much like 2I/Borisov, this object may share characteristics with long-period comets in our own system. Yet the sheer scale of it sets it apart, hinting at reservoirs of material in other planetary nurseries that dwarf those in the Kuiper Belt or Oort cloud. If 3I Atlas is representative of a broader class of massive interstellar comets, it suggests that the galaxy is seeded with planetesimal-sized wanderers that drift between the stars, carrying the chemical fingerprints of their birthplaces. The implications for planetary science and astrobiology are immense. If such objects are abundant and large, they could play a role in spreading the basic ingredients of life across the galaxy. The panspermia hypothesis, long a fringe idea, posits that microbial life or its building blocks could travel across interstellar distances aboard comets or asteroids. While unproven, the existence of massive objects like 3I Atlas makes the logistics of such transfers more plausible. Large bodies provide more shielding from cosmic radiation, more insulation for volatile compounds, and greater stability during long journeys. If complex organic molecules are detected on this object, it could strengthen the idea that the galaxy is interconnected not only through stars and gravity, but through chemistry and biology. There is also the broader cosmological significance. By measuring the size and properties of 3I Atlas, astronomers can refine estimates of how many interstellar objects are wandering through the Milky Way at any given time. Before Oumuamua, the assumption was that such visitors would be exceedingly rare, perhaps one detectable in centuries. Yet 3 confirmed detections in just a short span suggest they are far more common. The fact that one of them is as large as 3I Atlas changes the scale of the population. Instead of a galaxy filled only with dust and small debris, it may teem with boulder-sized, mountain-sized, and even larger wanderers silently moving in the darkness. This recognition transforms interstellar space from an empty gulf into a dynamic and populated environment. The James Webb Telescope's role in this discovery underscores why it has become the most transformative astronomical instrument of our era. Its infrared sensitivity allows it to detect faint heat signatures and subtle spectral features that ground-based telescopes cannot. With 3I Atlas, Webb has not only measured its size but also provided data that helps scientists build models of its density, reflectivity, and surface characteristics. This level of detail is unprecedented for an object hurtling through space at extraordinary speeds and staying within observational range for only a limited window of time. Every day matters when tracking such a visitor, and the Webb's capacity to gather high-resolution data quickly has proven invaluable. One of the fascinating aspects of Webb's confirmation is how it adds depth to the narrative of interstellar exploration. Human culture has long imagined alien worlds and visitors, but in reality, the galaxy itself delivers fragments of those alien systems right to our doorstep. 3. I-Atlas is not a planet, not a spacecraft, but it is undeniably alien, formed under a different sun, in a different nursery of gas and dust, and now crossing paths with our solar system. The revelation of its immense size makes this encounter even more dramatic. We are not merely observing a pebble from afar, we are witnessing a mountainous relic from another corner of the cosmos glide through our skies. The detection also reinvigorates discussions about the potential for future missions to intercept interstellar objects. While 3I Atlas itself may already be too far and too fast to reach with current technology, its discovery highlights the need for preparedness. If such large objects are more common than once believed, then with the right early warning systems, space agencies could plan missions to rendezvous with them. Studying an interstellar body up close would be equivalent to reaching another solar system without leaving our own. It would provide ground truth to complement Webb's spectral observations and open the door to analyzing samples from beyond our stellar neighborhood. There is also a cultural dimension to this discovery. Humanity is at a moment where the boundaries of knowledge are being stretched daily by tools like the James Webb Telescope. The realization that interstellar objects are both more common and more massive than expected taps into a deep sense of wonder and humility. For centuries, people speculated about what lies between the stars, and now the stars themselves seem to be sending emissaries, chunks of ancient worlds laden with secrets, to answer those questions. 3. I-Atlas, in being larger than expected, serves as a symbol of how reality often surpasses imagination in scale and complexity. The revelation also sharpens the sense of urgency in cataloging and understanding these objects. If interstellar bodies of this size cross paths with our solar system more often than assumed, they are not only opportunities for science, but also potential hazards. A body the size of 3I Atlas, if it were on a collision course with Earth, would carry devastating consequences. While the probability of such an event is vanishingly small, the recognition that such large visitors exist adds weight to planetary defense discussions. Understanding their trajectories, compositions, and behaviors becomes not only a matter of curiosity, but of preparedness. Beyond risk and exploration, the discovery enriches the broader field of comparative planetology. By analyzing 3I Atlas, scientists can directly compare materials from another solar system with those of our own. Are the ratios of ices, silicates, and organics similar? Do the spectral signatures suggest different conditions of formation? These comparisons help test theories of planetary evolution and migration. For instance, if 3I Atlas has more carbon-rich compounds than comets in our system, it may indicate that its home star formed in a more carbon-dense environment. Each data point becomes part of a galactic mosaic, painting a picture of how stars and planets come into being across the Milky Way. The fact that Webb confirmed 3I Atlas to be so much larger than expected also demonstrates the limitations of earlier telescopes and observational methods. Without Webb's capabilities, we might still assume this object was relatively small and unremarkable. Instead, the telescope has once again revealed hidden dimensions of the universe, reminding us that even when we think we understand, reality holds deeper layers. This lesson extends beyond astronomy, serving as a metaphor for the pursuit of knowledge itself. Every new lens we build shows us that what we thought was small may in fact be vast. What makes this discovery especially engaging is the sense of immediacy it conveys. Unlike distant galaxies or faint echoes of the early universe, 3I Atlas is here now, passing through our solar system in real time. The Webb's confirmation of its immense size transforms it from a fleeting speck of light into a monumental cosmic visitor. It is as if a mountain from another world has wandered into our backyard, offering only a brief glance before vanishing again into the void. This fleeting encounter underscores the importance of vigilance, of always watching the skies, because the universe continues to deliver marvels without notice. As scientists pore over the data, one cannot help but sense the unfolding of a new chapter in humanity's relationship with the cosmos. The Webb telescope, designed to peer into the earliest epochs of the universe, is now also rewriting our understanding of the immediate galactic environment. 3I Atlas, larger than expected, embodies the unpredictable richness of discovery. Each interstellar visitor teaches us that the galaxy is not a static stage, but a living, dynamic arena where worlds and fragments of worlds move across unimaginable distances. In confirming the true scale of this object, Webb has not only revealed the size of a comet, but has also expanded the scale of our imagination. The realization that 3I Atlas is far larger than earlier predictions has created a cascade of questions and possibilities that extend well beyond its physical size. This interstellar traveler is not just an object passing by. It is a messenger from another realm of planetary formation, carrying within its icy and rocky body the fingerprints of processes that unfolded light years away. The James Webb Telescope has made it possible to glimpse the reality of its structure in a way that transforms how scientists view the richness of material scattered through the galaxy. Far from being a minor addition to the catalog of interstellar wanderers, 3I Atlas stands as a monument to the complexity of the universe and the depth of knowledge still waiting to be uncovered. One of the most compelling aspects of Webb's observations lies in the detail it has given astronomers regarding the thermal properties of 3I Atlas. By observing the object in the infrared spectrum, Webb can detect the heat it emits, no matter how faint. These measurements allow researchers to infer the thickness of its icy shell, the potential layering of materials beneath the surface, and the rate at which sunlight warms and then re-radiates from its body. A larger-than-expected object means that its ability to retain heat differs from smaller comets or asteroids. It can harbor pockets of volatile gases and complex compounds deep inside, shielded from the erosive radiation of interstellar space. This possibility has led to the notion that 3I Atlas might be less of a frozen lump and more of a reservoir, an interstellar archive of chemistry from its home system. The sheer scale of 3I Atlas also introduces new challenges in modeling its dynamics. Smaller objects can be easily perturbed by radiation pressure, outgassing, or gravitational nudges from planets and stars. A body of this magnitude, however, carries inertia that resists those influences. Its trajectory through our solar system thus provides a clearer record of the forces that acted on it over millions or billions of years. Scientists are carefully mapping its orbit with Webb's precision data, hoping to trace backward through space to approximate its point of origin. While pinpointing a specific star system is nearly impossible, narrowing the search to a region of the Milky Way may be feasible. In doing so, 3I Atlas could become the first interstellar object linked not only to our solar system, but to a broader galactic context, bridging the gap between distant stellar nurseries and our observational reach. Another layer of significance comes from the surface composition Webb has detected. The spectra hint at unusual ratios of water ice, carbon compounds, and silicate dust compared to comets in our solar system. These variations act as chemical signatures of its birthplace. Each star-forming region in the galaxy leaves its own imprint on the materials that condense into comets and planetesimals. By analyzing those patterns, researchers can compare galactic chemistry in a tangible way, testing whether processes in our solar system were common or unique. The confirmation of 3I Atlas's larger size means there is more material to study, more surface to examine, and a stronger signal from which to glean insights. It is as though the galaxy has delivered a chunk of its own history for us to read. The larger mass of 3Y Atlas also hints at greater durability. Traveling through interstellar space is no gentle journey. Cosmic rays, collisions with micrometeorites, and the sheer emptiness all conspire to erode and damage small bodies. Many fragments are likely reduced to dust long before they reach another star. For something of 3I Atlas's size to survive the voyage intact suggests resilience and raises questions about the conditions that allowed it to endure. Was it expelled relatively recently on a cosmic timescale? Or has it been wandering for billions of years, its surface weathered but its core preserved? Webb's ability to probe beneath the outer layers with spectral analysis may eventually help answer this, revealing whether its chemistry reflects ancient origins or a more youthful ejection. On a more conceptual level, the discovery of 3I Atlas's size forces a rethinking of how scientists classify interstellar visitors. Oumuamua was puzzling because it appeared elongated and lacked a cometary tail, challenging existing categories. Borisov resembled a traditional comet but was smaller in scale. Now 3I Atlas presents yet another paradigm: large, massive, and chemically complex. If such diversity is already apparent in the first 3 objects ever observed, then the range of possible interstellar bodies must be vast beyond imagination. This points to a galaxy teeming with an almost infinite variety of planetary fragments: shards of ice, mountains of rock, mixtures of organic material, and combinations no one has yet conceived. Each detection expands the catalog and redefines the possibilities, turning interstellar objects into one of the most exciting frontiers of astrophysics. The implications spill into the discussion of galactic ecosystems. Stars do not exist in isolation. They form in clusters, evolve and die, scattering material across space. Large objects like 3I Atlas are evidence of that ongoing exchange. Our solar system is not a closed box, but part of a wider cosmic economy in which matter is traded between stars through gravitational slingshots and collisions. By studying these messengers, scientists gain not only a snapshot of other systems, but also insight into the grand circulation of matter in the galaxy. This understanding helps refine theories about how elements and compounds crucial to life are distributed across stellar populations. In this sense, 3I Atlas is more than a visitor. It is a participant in the grand dialogue of galactic evolution. The detection of its immense size also has technological implications for astronomy. It underscores the importance of early identification and rapid response. Interstellar objects travel at extraordinary velocities, and their windows of observability are narrow. If Webb had not been operational, we might never have realized just how large 3I Atlas is. Future observatories, both space-based and ground-based, will need to be designed with this urgency in mind. Projects like the Vera C. Rubin Observatory, which will scan the entire sky repeatedly, may catch even more of these wanderers earlier in their journeys, providing the time necessary to mount in-depth studies. The lesson of 3I Atlas is that opportunities to study interstellar objects are fleeting, but the rewards are immense if we seize them. Cultural and philosophical reflections inevitably follow such a discovery. When humanity looks at 3I Atlas, larger and stranger than expected, it sees not just an object, but a mirror of its own curiosity. The galaxy is not an empty gulf, but a place alive with exchange, surprise, and discovery. Each new piece of data forces us to stretch our imagination and rethink assumptions. What else drifts in the dark between stars? How many colossal wanderers have slipped past unseen in millennia of human history? The Webb's revelation turns what might have been a minor astronomical event into a transformative moment of awareness. It reminds us that the universe is not static or predictable, but a dynamic arena where new wonders constantly appear. There are also practical considerations for planetary defense and long-term space exploration. If objects as large as 3Y Atlas are part of the interstellar population, they represent both an opportunity and a hazard. Though the likelihood of impact is minuscule, the potential energy carried by such a mass moving at interstellar speeds would be catastrophic if a collision occurred. This knowledge adds weight to ongoing discussions about planetary defense infrastructure, early detection networks, and international cooperation. Conversely, if humanity develops the capability to intercept or study these objects, they may become stepping stones for deep space exploration. Their resources, water ice, metals, and carbon compounds, could be harvested to support human missions beyond the solar system. In this way, 3I Atlas not only symbolizes discovery but also hints at a future where interstellar visitors become part of humanity's own journey outward. The story of 3I Atlas also reinvigorates the search for exoplanets and the study of star systems in formation. If such a large fragment could be ejected and survive the journey across interstellar space, it suggests that planetary formation processes routinely produce material robust enough to escape. This strengthens the case that planetary systems everywhere are dynamic and unstable in their youth, expelling significant amounts of debris. By studying 3I Atlas, astronomers may refine their understanding of those early chaotic epochs. It offers a direct piece of evidence for the violence and dynamism that shape planetary systems, something that until now has been inferred mostly from simulations and indirect observations. Webb's revelation also sharpens our sense of scale. Astronomical discoveries often deal in abstractions, billions of light years, trillions of stars. But 3I Atlas brings the enormity of the universe down to something more tangible. It is a single, massive body passing through our solar system, a physical reality that can be measured, observed, and analyzed. The recognition of its true size makes it less a distant abstraction and more a visceral presence. It is as though the galaxy itself has placed a stone at our feet, challenging us to examine it closely and see what stories it tells. What is striking about this discovery is that it reshapes not just scientific models but also human imagination. Science fiction has often imagined derelict ships, alien artifacts, or planetary fragments drifting between stars. Now reality has delivered something not far removed from those visions. 3I Atlas is not a creation of fiction but a fact of the cosmos, and it is larger and more complex than we dared to expect. The Webb's confirmation reinforces the lesson that reality consistently outpaces speculation. For every mystery we solve, another opens wider and deeper than before. The enlarged scale of 3I Atlas also raises intriguing questions about how such bodies interact with interstellar environments. Does a larger surface area allow it to collect interstellar dust and particles as it travels? Could it accumulate layers of material from different regions of the galaxy, becoming a stratified record of its journey? If so, analyzing its surface could provide not just a window into its home system, but into the environments it passed through on its way to us. Webb's instruments are capable of detecting subtle features in its spectral signature that might hint at such layering, offering the tantalizing possibility of reading a travelogue written in ice and dust. Beyond the technical and scientific, the encounter with 3I Atlas inspires reflection on humanity's place in the universe. Here is a massive body, older than any civilization, formed around a star we may never see directly, and yet it crosses our path now, in this fleeting moment of human history. The odds of such timing are staggering, and yet it has happened not once, but 3 times, in just a few years. This coincidence suggests that we are only now becoming capable of seeing what has always been there, that the galaxy is alive with motion and interaction, and that we are participants in that grand stage, whether we realize it or not. The larger size of 3I Atlas also sharpens the question of how many similar bodies are still out there. Astronomers can now adjust their estimates upward, calculating that for every small interstellar object, there may be many larger ones moving silently through space. The Milky Way, then, is not just a starry expanse, but a vast ocean populated with uncharted islands of rock and ice. Each one represents not just an astronomical curiosity, but a potential key to understanding the processes that shape worlds, distribute elements, and perhaps even seed life. The Webb telescope's confirmation of 3I Atlas's true scale is not the end of a story, but the beginning of many. It opens pathways of inquiry into planetary dynamics, galactic chemistry, astrobiology, and even philosophy. It reminds us that the cosmos is not a distant spectacle but an active environment filled with surprises that come to us unbidden. The discovery does not end with the recognition of size. It resonates outward, prompting new ideas, inspiring new missions, and reshaping our understanding of what it means to live in a galaxy alive with wandering giants. The confirmation that 3I Atlas is significantly larger than astronomers initially believed continues to open new threads of inquiry, each one branching into unexpected areas of science and thought. Its size is not just a fact measured in kilometers. It is a key that unlocks questions about the physics of interstellar travel, the chemistry of alien star systems, and the potential role of such objects in shaping cosmic history. The James Webb Space Telescope's ability to reveal these truths underscores the extraordinary advantage of modern instruments, and it highlights how much of the galaxy still waits to be discovered. Another avenue of exploration is the role of collisions in shaping such a body. A mass as large as 3Y Atlas could be the remnant of an ancient impact in its native system. When protoplanets collide, they generate enormous debris fields, ejecting fragments into surrounding space. Some of these fragments may be small, but others, like 3I Atlas, could be mountain-sized. The ejection of such massive fragments suggests a system where violent processes dominated, reshaping planets and scattering material across interstellar distances. If Webb's data show irregularities in the object's shape or unusual mineral distributions, they may be evidence of a cataclysm that forged it, telling the story of a planetary disaster that occurred millions or billions of years ago in a faraway solar system. The fact that 3I Atlas has reached us also sheds light on galactic dynamics. Interstellar space is vast, and the odds of any single object crossing paths with our solar system are infinitesimal. Yet with Oumuamua, Borisov, and now Atlas, the pattern is clear. Interstellar debris is abundant. The discovery that some of this debris comes in massive forms suggests that stellar neighborhoods are more connected than once thought. The gravitational pull of stars as they orbit the galactic center creates constant exchanges of material, tossing bodies from one system into another. In a sense, the galaxy operates like a great mixing bowl, ensuring that matter from one corner can eventually find its way across unimaginable distances. Webb's confirmation of Atlas's scale adds to this picture by showing that even large fragments are part of this exchange, not just tiny grains of dust. One cannot overlook the influence of such discoveries on the philosophy of cosmic life. A body this size could carry vast reserves of water and carbon compounds, the basic ingredients for biology as we know it. If those compounds formed in another system, they demonstrate that prebiotic chemistry is not unique to our solar system, but a universal process. That raises profound questions. Could worlds elsewhere have been seeded by material from interstellar objects? Could Earth itself have received some of its carbon or water from a body like 3I Atlas billions of years ago? These ideas remain speculative, but the larger the body, the more plausible it becomes that it could shield fragile molecules during long voyages and deposit them intact upon impact with a planet. Webb's observations also allow scientists to compare 3I Atlas with the Kuiper Belt objects and Oort cloud comets that orbit the Sun. If Atlas shares similarities with these populations, it suggests a universality to planetary formation. But if its chemical fingerprint is distinct, it could prove that not all systems build their comets the same way. Already, preliminary data indicate subtle differences in the ratios of carbon dioxide, water ice, and silicates compared to known solar system comets. This difference may hint at variations in the temperature, density, and metallicity of the star-forming region where Atlas originated. It is, in essence, a sample from another kitchen in which the recipe of planets was written differently. Beyond chemistry, size plays a key role in how interstellar bodies interact with stellar systems they encounter. Smaller objects can pass unnoticed, their faint signatures blending into background noise. Larger ones like Atlas, however, can be studied more thoroughly. They also experience stronger gravitational influences when passing near stars, altering their trajectories more dramatically. This means Atlas may have interacted with other stars before reaching us, each encounter shaping its path like a cosmic billiard ball. Tracing these deflections backward could help astronomers identify which regions of the Milky Way contributed to its journey. piecing together a trail of stellar interactions that stretches across light years. There is also a fascinating possibility that 3I Atlas represents not just a fragment, but a type of object entirely unfamiliar to our solar system. While its composition appears comet-like, its sheer mass and survival suggest it could be part of a class of interstellar supercomets or megaplanetesimals. If such bodies are common, they may play roles in seeding young star systems with essential materials. During the early days of a star cluster, when stars form in close proximity, massive bodies like Atlas could be exchanged between systems, delivering exotic compounds that shape the chemistry of forming planets. In this sense, the galaxy itself functions like a cooperative nursery, where no star is entirely isolated from the contributions of its neighbors. The discovery also redefines how astronomers estimate the population of interstellar bodies. Earlier assumptions were based on smaller detections, suggesting that such visitors would typically be modest in size. Webb's revelation forces a recalibration. If large bodies exist and are detectable, then their numbers may be higher than projected. That means interstellar space may be filled with more potential targets for observation, and the odds of another encounter in the near future rise significantly. Each encounter offers a once-in-a-lifetime chance to learn about galactic diversity, but it also builds toward a statistical understanding of how common such bodies are. The more we find, the clearer the picture becomes. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on James Webb's 3I Atlas discovery being bigger? We want to hear from you. Thank you for watching and see you next time.